So coming to our first problem, sample problem 2318. So it is the same problem that we have solved in section 2.2, and in that section we analyzed this circuit for its current and voltage values. And as you already know, the values, the supply voltage is given and the impedance values of inductor and resistor are given, and we already have calculated the values for total impedance, the current through the circuit. There is only one branch, so the current we have calculated, and in addition we know the voltage drop across each element. Right, so once those values are given, the question is about the power components, namely apparent, active and reactive power consumed by each element. You have to, which means in that case you have to consider resistor as a single element and inductor as another element. So for each element you have to calculate apparent, active and reactive separately. In the part B, it asks the same power components consumed by the load when you consider these two components not as two individual elements but as a single element. So in that case you have to calculate the apparent, active and reactive power components, considering that this entire load is not two different elements but a single one. So that is the problem, and let's go to the answer. And before going to the answer, I would like to discuss about the theory behind the apparent power, active power and reactive power. So let's go through one by one. And apparent power, so maybe if you have gone through the class note 3, you are already aware of the definition of apparent power, and it's really easy because it is much similar to the power in DC system. So you already know that power in DC system is P equals VI. Here as well, so the apparent power is V times I, and there is a small difference. In this case we are using the conjugate of the current, right? That's the first thing you should notice here, the star. And the second thing is these components are, the first thing you should notice is the star mark here, and the second thing you should notice is these components are complex values. This V and I are complex values, right? So you need to know the complex voltage and current values through the element. So, and again, this V doesn't mean the source voltage. You must know that V is not the source voltage. For an instance, if you are going to calculate the power consumed by this device, you should know the voltage drop across that element and the current through that element, right? So you should know the current through that element and you should know the voltage drop across that element. So that you must keep in your mind. So most of the time, one very common mistake that a student would do is they use the supply voltage instead of the voltage drop across this element, right? So coming back to apparent power, you must know that this voltage and current components are through the element, and you're not going to multiply the voltage by the current value but the conjugate of the current value. Now if you have followed the complex number theory, you know what a conjugate of a complex number is, but don't worry if you don't know, it's really easy. Um, as you are aware, so in this graph here I have, for an instance, I have taken a complex number, an arbitrary number. So it is z equals 360 plus 270i, right? And it's some point sitting on the complex plane, and these are the Cartesian form. Sorry, this is the Cartesian form, right? So I'm not going to write the entire word, and the same complex number I can denote using the magnitude and the angle, so that we call polar form, right? So so if the complex number, if your complex number is given in Cartesian form, right, all you have to do is take the sign of the imaginary part and invert it. So in this case, the sign value of the imaginary part is plus 270i, right? So all you need to do is invert it. In that case, you would get negative 270i. So the conjugate would be therefore 360 minus 270i, right? So the conjugate of this complex number here would be this one, right? So it's really easy, and if your complex number was in polar form, all you need to do is, so let me write this complex number in polar form. It is the same complex number you are seeing here. So it's in polar form, it's going to be 450, and the angle is 36. I'm not going to write the decimal places, right? So if you're going to find the conjugate of this thing, all you need to do is take your angle value and invert the sign of the angle value. So in this case, the sign would be plus. It's a positive 36. So you're going to invert it, which means it's going to be negative, right? So remember, I'm not talking about the inverse. This should be negative 36. It's really easy. So this is all you have to do. And in theory, what this means is you are going to take the mirror image of this z point, right? You're going to take the mirror image of this z point through the horizontal axis, right? So you're going to find the mirror image. So the mirror point would be here, and that we call the conjugate. So in that case, you realize that the real part is not going to change, only the imaginary part is going to change. In this case, if I consider this complex number, to take the image, I have to change the sign of this imaginary part. It has to be negative. So the only thing I need to do is invert the sign of the imaginary part. So if it is the angle, I have a plus angle here, so I need to look for the negative angle. That's all you need to do. So it's really easy, as I said. And there's another thing you should notice, that if you find the conjugate of z, which means you have the conjugate of z and you're going to find the conjugate of that one, you would get again the same z value, this one. So which means you're going to find the image of this thing, so it's obviously going to be the original point. So that's something extra. So if you didn't catch that part, the last part, the conjugate of the conjugate, so don't worry, forget that thing. I don't think that's going to be that necessary for this section, but it's always better to know more. So for an example, I would like to find the conjugates of these values. So here this is a real number, which means I can write this as 360 plus 0i or 0j. Imaginary part is 0, so it doesn't matter whether you have a plus sign or minus sign there, because this part is always 0, and therefore the conjugate of 360 is going to be again 360. So it doesn't matter whether it is negative 0i or plus 0i, it's always going to be 360, and that is the case for any real number. The conjugate would be the same. And if you go to this part here, you can see it's a plus sign. So the conjugate, in the conjugate, the only thing you would do is you take the imaginary part, it's going to be plus 50i, and you're going to invert the sign, which means you make negative. Now it's going to be negative 50i therefore, and you have 360 in front of that. So the conjugate of this second one is going to be 360 minus 50j, right? So likewise, it's really easy, and let me do that this one as well. So it's a little bit different, 2j, and so this is going to be 0 plus 2j. You don't really have to write this 0 value, it's not necessary, and you're going to invert this sign, which means you get 0 minus 2j. So the conjugate of this 2j value is negative 2j, right? And let me do another one, maybe this one here, right? And I think it's obviously you are going to change the sign of the angle, and you are making minus angle positive, so it's going to be 25 positive 29, right? So graphically what it means is, for an instance in this case 2j, so 2j is going to be somewhere here, right? So in the positive direction, this is your 2j, and you're going to take the mirror image, so it should be now in this direction, right? And it should be negative 2. So here you have positive 2, and remember this is not in the same scale, right? So not to this scale, but this is the idea, right? So all the other numbers, if you would draw them on the complex plane, you would understand we're talking about the same principle here. You're looking for the mirror image through horizontal axis, right? That is apparent power. So now coming back to apparent power, you should know what is the conjugate mean, what does it mean, and how to calculate the conjugate once you are given the current value. So all you do is you take the voltage value, substitute that value, the complex form, and multiply it by the conjugate of the current. So you find the conjugate of the current and substitute it there. Now you have a multiplication of two complex numbers. So if you know the complex number theory, maybe you can solve it using that theory, or else don't worry, you can always use the scientific calculator and simplify this, right? So basically that is the apparent power, and as you may kind of have an idea already about complex numbers, so the multiplication of these two is going to result in another complex number, right? So therefore you must know that the apparent power is a complex value, which means it may in the form real plus imaginary, right? So there would be j. So it would always accompany a real part and imaginary part. It doesn't mean that it can't be real only. There would be situations, but still in general the apparent power would be a complex value, right? So keep it in mind. And the next thing you must know is like that the unit we are going to use to measure apparent power is volt ampere. It could be kilovolt ampere, megawatt ampere, or anything. You may have any prefix you want, but the basic unit would be volt ampere. Right. So going to the next component, active power. So in principle, it is the real part of apparent power. So in the early section, I told you apparent power is a complex number. So which means you would either use the Cartesian form or as the polar form to denote apparent power. Right. So one of these two forms you can use, and in that case, if you want, once you have the apparent power, if you want to calculate the active power, all you need to do is look for the real part of your apparent power. Take the real part of this thing, right? So for an instance, say like your apparent power is 100 and angle is, let's say, 30, right? Let's say this is the case. Now one thing you could do is, if you want to take out the real part of this thing, one thing you could do is you can use the calculator. You can enter this value in the calculator, 130, and you would directly get the real part, because calculator would convert it to the real plus imaginary form. So then you can directly read the real part. So in this case, the real part is 50 times root 3. It's really easy. And there's again a function to find the real part, I think. Okay, no, you can convert it to the Cartesian form. In some calculators there is a function to find the real part as well. So for an instance, let's say your number was in the polar form, so in that case you can simply convert it back to Cartesian form. So then it's going to be real plus imaginary parts you can take out from the answer. And again, another method is like in the Cartesian coordinates, so this means you have a 100 length line and the angle is 30. This angle is going to be 30 degrees. Now you know the real part means the projection on real axis, and the imaginary part is this one. So this length is going to be the imaginary part, and this length here is going to be the real part. So now what you have is simply a rectangular triangle, and you know this length, you know this angle here. So what you want to know is this length. I think this is simply ordinary level knowledge, and you can calculate this using the cosine value of 100. So then this value is going to be the active power for this considered case. If the apparent power was this much, the active power would be the length of this AB leg of this triangle, right? So in general, we can use this as an equation like shown here. So let's say this is the magnitude and this is your angle phi naught. So for any given apparent power value in the form m phi degrees, this would be the equation you're going to use to calculate the active power. So simply what you are again doing here is taking out the real part. You are looking for the real part of this complex number. So it would be very much easier if you get the apparent power in Cartesian form, because you can clearly see the real part directly. You can see the real part there, right? So in the same way, if you go for the reactive power, you have to take out the imaginary part. So which means in your triangle, this is this. If you look for the same case before, what you have to look for is this length here. This is going to be the imaginary part. So in general, if your complex value is in polar form, you can use this equation, and you are lucky if your apparent power is in Cartesian form, because you can directly take out the imaginary part. I hope it's clear by now. So another thing you should notice here is that active power is real. You are looking for the real part. Reactive power is imaginary. You are looking for the imaginary part. So which means it can sometimes accompany with this imaginary. To denote it's an imaginary value, it may have j in front of it, j or I. So, but it's not necessary, because usually people know that reactive power is imaginary, and sometimes it is also known as imaginary power, and this sometimes known as real power. Active power is sometimes called real power, and reactive power is sometimes called imaginary power because of this thing. And usually people in the field know that it's imaginary. And in summary, what you should keep in your mind is that the apparent power is a complex value, which means either you have write it in the form p plus jq, or else it's polar form. And in theory, from the first principles, this is the way to calculate apparent power. It's going to be the multiplication of voltage and conjugate of the current in their complex form. And it's okay sometimes it is okay to just to denote the magnitude of the apparent power. In most cases in the industry, you won't see the angle, or as the angle value of the apparent power. So in most cases you would just go with the magnitude. You would see the magnitude because it's really not necessary. Once you know the power factor, which we are going to talk in a while, and any other power component related to that device, you can calculate this angle. So it's possible. Therefore, people usually do not go with the angle. Maybe another reason for not to denote the angle is there are two different units which are well known to measure angle. One is radian and the other is degrees. So therefore, to avoid any confusion between the units, maybe they are not using the angle value, for some reason they are avoiding using the angle. And the next thing is the unit of apparent power is going to be volt ampere, and you may have any prefix like kilovolt ampere. So, and whenever in equations or somewhere, whenever you symbolize apparent power, you use the letter S. As a thumb rule, you use letter S to denote apparent power. You can go with any symbol you would like, but as thumb rule, people use S. Right. And coming back to active power, you must keep in mind that it is a real number, and you will never ever see active power with an imaginary, which is an imaginary number. So it's not going to happen. Yeah, basically it can't happen. And if your apparent power is given in the Cartesian form, it's simply the p value. If it is given in polar form, you have to look for the m cos phi, right? And let's say you have been given the voltage and current values in their complex form. For an instance, you know the voltage, the complex value, and the current complex value. In such situations, you really don't have to calculate the apparent power first. Maybe that's one method. You can, as the first method, you can calculate the apparent power and then take the real part out of it to calculate the real power. It's one way you could do, but there is a simple method which you can directly go for active power. In that case, what you would do is you take the magnitudes of these two and multiply them. Right? For an instance, let me take an example. You have a voltage value which is going to be simply, let's say, V times angle is phi V, and you have a current value I times, and the angle is, the magnitude is I, angle is phi I, the argument is phi I. So this angle of a complex number, sometimes we call, of course we call argument, right? And in such situation, what you need to do is to calculate active power directly. You can use this equation here, and it's going to be V I cosine of the angle difference between these two, right? So that you can calculate using phi V minus phi I, right? So this difference between these angles, sometimes we call the power angle. The same thing you call power angle, right? So this phi V minus phi I you call power angle, right? So similarly, for the reactive power, it's going to be an imaginary number, but not necessarily, it's really not necessary to use the letter J or I in front of that. So because everybody knows that it is an imaginary value, that's why it is called imaginary power sometimes. And you use the letter Q to denote your imaginary power or as reactive power in equations, and letter P to active power. And units are very important. To measure active power, you use watt. So you are already familiar with watt unit from the previous section. So it is the power that is dissipated from a system, the visible power. Like for an instance, if you consider a resistor, the heat that it dissipates is measured in watt. So in this case as well, we are using watt to active power, so you should get an idea that here as well we are talking about the heat which is visible. And imaginary power, on the other hand, is not visible, it's imaginary. That's why we use the word imaginary. So it is some sort of power that which is oscillating between the source and the load, and we use the unit var, var, to measure imaginary power. And you may see any prefix in front of that, like kvar, kilovar, or megavar, etc. And in summary, these things you should remember and are going to be very helpful in the time to come. So I hope you understood. So if you have any question, you may go through the reference notes. And right, so let's go back to our problem. So with that knowledge, we need to find the apparent and active and reactive power components for this circuit. Right, let's try to answer the problem. And in the part A, it asks for the apparent, active and reactive power components to each element. So in this section, in this part, we have to calculate for each resistor and inductor the apparent and active and reactive power. So let's proceed with the first part, the first element, resistor here. And as you can see, we already know the voltage and current. So if in order to, let's say we are going to find the apparent power of this thing, so SR, and for that we need to know the current through this element and the voltage drop across this element. These two things we need to know, and fortunately we have already calculated them from the previous section, and you should be able to calculate such things by analyzing the circuit by now. And if you still don't know, I highly recommend you to go through the previous section, which is section 2.2, electric circuit analysis, and that is something where you should master your skill before coming to the power in AC systems. So for this problem, fortunately we don't have to find these components, and we know what is current value and the voltage drop value in their complex form. So that's something again you must notice. You need to know the complex values of the current and voltage, otherwise you can't calculate the apparent power completely. Maybe you would be able to calculate the magnitude, but to calculate the angle you must know the complex form. Right, so I'm going to substitute these values here, 46 times root 5 for the voltage, and the same magnitude divided by 5 for the current, and I'm going to substitute them with the angles. Right, so right, this is the voltage value, this is the current value, and you must notice that I'm taking the conjugate of the current. So the first thing I have to do is find the conjugate of this thing, conjugate of the current. So if I take the current value out, it's 46 times root 5 divided by 5, and the angle is minus 63 point something, right? And you know, if the complex number is in polar form, to find the conjugate, all you have to do is invert the sign of the angle. So in this case I have to make the sign positive, so it should be positive 63 point something. So that I have done here, and I get the conjugate of my current as 46 multiplied by root 5 divided by 5, and the angle is 63.435 degrees. So now I know the conjugate of the current and the voltage value. So to simplify this multiplication more, I can use the calculator. So in that case, what I have to do is input these values one by one in the calculator. Root 5 times, and the angle is negative 63.435, and I have to multiply that by 46 times root 5 divided by 5 and take the positive angle 63.435. right, so I get the answer. It's 2116. So the same answer, and of course it is a real number, as you can see, and you can write it in the polar form. Therefore the real number 2116, sorry, 2116, you can write in the polar form like this. And if you are going to use the Cartesian coordinates, it's going to be 0i, so there is no point of writing 0 imaginary part. Therefore you can simply write just the real part, which is 2116. right, so here I have used the polar form because in that way I feel it I get the sense of complex number. So it really is a real number. Still it's a real number, though I have written it in the polar form. It's still a real number. And if you have followed the complex number theory, you know that real numbers are a subset of complex numbers, right? So you know the number theory, and complex number set is there, and real number is a subset of this. So I can write it, in fact definitely I can write it as in the polar form, so no worries. And right, now we have found the apparent power through our resistor. So this would be the apparent power, and it's, remember that it's in volt ampere. And now what we have to do is find the active power. And once you know the apparent power, to calculate the active power, all you have to do is take out the real part of this. Take out the real part. Right. So I have to take out the real part of this number, and I know it's the whole number is a real value. So therefore my active power would be 2116 watts. Right, so I really don't have to go through all the methods how to calculate the real part of a complex number, because this value here is, I'm pretty sure that it's a real number. So if you want, definitely what we are talking about is you have the real number plane, sorry, real number axis, and on that axis you have a line with 0 angle. Length is 2116, so it's a real number. And right, on the complex plane, this is what we are talking about. Right, so right, and if I am to calculate the reactive power, or as imaginary power, I have to take out the imaginary part of my complex, or as apparent power, right? So apparent power is complex number, complex value, and I already know this is a real number, therefore it doesn't have an imaginary part. So if I write it in the Cartesian form, this is it is true that my imaginary part is 0. Therefore it is pretty clear, I'm pretty sure that my reactive power is 0, right? So it's going to be 0 R. So therefore for the resistor, my apparent power is this value, and since apparent power is a real value, it's going to be equal to the active power. Since there is no imaginary part in the apparent power, my imaginary power, or as reactive power, is going to be 0. Right. Now if we go to the inductor, for inductor as well, we have calculated to calculate the power components, you should know the voltage drop, the current too, right? If you know these two, you can calculate the power components too in the inductor. And fortunately, again, we have calculated those two, so all you have to do is substitute them in the correct way, in the correct order. And the first thing we would do is, like we did in the earlier case, calculate the conjugate of the current. So here as well, you are using the same current, so no worries. You are going to invert the sign and you get this value, right? You get this value for the conjugate. And again, to simplify this multiplication, I'm going to use the calculator. So it's 92 root 5. The angle is 26.565 multiply 46 times root 5 divided by 5, and the angle is 63.435. right. All I get is an imaginary number, so it's going to be 4,232. right. So the same number in polar form I have written here, so these two are not two different numbers, they are the same, and in that way it feels like a complex number. That's why I am using the polar form here, and it's going to be 4,232, and the angle is 90 degrees volt amperes. This is the apparent power. Now we have calculated the apparent power. Apparent power for inductor is okay. Now to calculate active power, what you have to do is take out the real part. Right. So we have already discussed what are the methods to take out real part from this thing, and in this case, since we already know that this is an imaginary number, the real part of this thing is 0. Therefore, the active power is 0. It's going to be 0 watts. And in the same way, if we are to calculate the reactive power, all you need to do is take out the imaginary part of your apparent power. In this case, the power itself is an imaginary number, so the total amount is equal to the amount of apparent power is equal to the reactive power. So it's going to be 4,232 watt. So these two are the same. The reactive power is equal to the apparent power, right? So we have calculated the as required. We have calculated the apparent power, active power, and reactive power. So in summary, these are the values you would get for the resistor and inductor. The individual apparent, active, and reactive power components are like this, right? Now let me go to the second part. In second part, you have to consider this entire load as a single unit and then calculate the apparent, active, and reactive power components. That's what we are going to do next. So in part B, so for that as well, what you have to do is, all you need to know is the current, and the voltage drop across your load. So in this case, fortunately it's the supply voltage, because you are considering this entire series connection as a single load. So these two elements you are going to consider as a single load. So fortunately our voltage is the supply voltage. Current we have already calculated here. So we know the complex values of voltage and current. Now we can easily calculate apparent power. So you substitute the voltage value and the current value, and then you have to calculate the conjugate of the current value. Right, so you know how to calculate conjugate, and now to simplify this you are going to use the calculator. It's 230, and in this case, since the angle is 0, that means I'm entering a real number. So you can, if you want, you can enter the 0 value there, the angle, but it's really not necessary. I can just input the real number alone and then multiply it by our current value, 46.5 divided by 5. The angle is negative 63.435. Right, so I get my answer in Cartesian form. I would like to convert it to the polar form. Yeah, then I would like to have my angle in decimal as well. Therefore I'm going to convert between standard form and decimal form. So now this is the answer I get. Right, so the final answer is this value, 4731.5198 is the magnitude, and the argument is 63.435 degrees. So this is the apparent power. So if I consider this entire thing as a single load, so the apparent power it's consuming is going to be this much, exactly this much. Right, now we already know the apparent power for the total load. So to calculate active power, all you have to do is take out the real part of this. So you know few methods to take out the real part. Maybe you can enter this value to the calculator and look for the Cartesian form. So that's what I would usually do, or else you can take the magnitude and take the cosine of the angle, and there is another method. We discussed already these methods, and simply I would use this Cartesian form method, and in this case I can directly find the active power by taking out the real part. So in this case the real part would be this one, it's equal to the active power. So my active power of the entire load is 2115.9962 watts. Remember, the unit is watt for active power. So the next thing we need to calculate is the reactive power. Again, in order to calculate the reactive power, all you need to do is take out the imaginary part of this thing. So that I can do by taking the Cartesian form of this complex number, and I have it here, and take the imaginary part, which means this part. That's going to be the reactive power, and the unit is var. So it's going to be 4232.0018 vars. Right, and in summary, these are the answers for my second part, or as part B, when I consider the entire load as the entire, all the element as a single load. Right, and if you look back our results as a comparison, So as a discussion, these are the results we have. So these are the results from the first part, and this is going to be the second part. And you can clearly see, if you look at the active power from the resistor here, is very much close to the active power of our system, the entire load. And the reactive power, on the other hand, is very much close to the reactive power here. Sorry, these two I'm talking about. These are very close, not the same but very close. And apparent power is not the same because again, apparent power, if we happen to add up these two apparent powers, individual apparent powers, in this case 16, and I'm not going to take the zero angle because it's a real number, plus this value here, it's going to be 4232, angle is 90, and this value, if I convert back to polar form, you can clearly see it's very much close to our apparent power here. Compare these two values, you can see it's very much close, and the angle is almost same, right? So which means there is some relationship between when you consider the individual elements and several elements together in a circuit for the comparison of power. So in fact, in theory, these two results must be the same. For an instance, your active power in resistor, consumed by the resistor, should be the same as the active power consumed by the entire load. It should be same. It can't be two different things, because inductors are not going to consume any active power. Inductors are only reactive power consuming devices. So therefore, the only device in this circuit which is consuming active power is a resistor. Therefore, these two values must be the same, right? That's one thing you should notice. And of course, the other thing is, if you are to calculate the integration of several components, in this case you have two components, the inductor and the resistor. If you are to calculate the total power consumed, you don't really have to calculate the voltage and current like we did in this step, right? So you really don't have to. So in this step, in part B, what we did was we started everything from the beginning, voltage total and current total, and calculated everything from the beginning. But another approach you could have is simply, what you could do is, you already know the values, individual values, you already know the apparent, active and reactive power individual values. To calculate the total values, you could simply add them up. For an instance, we did the apparent power a while ago, and if in the same way, if I calculate the active power, total of the system is going to be the summation of individual apparent powers. So in this case, it's going to be 2116 plus, here we have 0. So it's going to be the same value, right? And similarly, if I am to calculate the reactive power, it's going to be the summation of individual reactive powers, and it's going to be 0 plus, here it's 0, 4232. Sorry, 232. I hope you get the idea by now. And it is war. Right. So likewise, the idea is that the power, like in DC, here as well, power is going to simply add up. You really don't have to care for the complex form unless you are going to find the apparent power. So for apparent power, you of course have to consider the complex form. Otherwise, if you are to calculate the active power or else reactive power in these two cases, right, they are special. Again, I'm going to note down. So apparent power and active power and reactive power, you can simply add up the individual power components and get the total power, right? So that is same for the reactive power. But for apparent power, you need to use the complex form. You cannot simply add these magnitude values and get the magnitude. Instead, what you have to do is you have to use the complex number theory and add these two values as complex numbers, and then you can get the apparent power, right? And there is another thing you could do. If you look carefully again, the total apparent power, if you convert back to Cartesian form, it's going to be this much. So which means once you have the total active power and total reactive power, total apparent power would be the summation of those two, and your real part would be the total active power, your imaginary part would be the total reactive power. So therefore, maybe in some situations you can use this knowledge. Therefore, you really don't have to know the individual apparent powers. Once you know the individual active powers and reactive powers completely, like in this case, so you could simply calculate the total apparent power, which is going to be sigma p individual plus j times sigma q individuals. I hope it is clear, and we have used that knowledge here to calculate total active power and the total apparent power at the end, total reactive power and the total apparent power, right? So note this thing in your mind, because this relationship is going to be very useful in some situations to simply solve the problem. So you could, if you use this method to answer part B, you can see it's really easy because it's a simple summation, and again it's simple algebraic summation, so no worries about complex number theory. So that's another thing, and yes, that knowledge you must possess. Now let's try to answer our next problem, which is problem 231b, and so it's again a problem that we have already analyzed in the previous section, and so ultimately we have been given the voltage value and the impedances values of each component. It's a bit complex problem compared to the previous one which we solved. Here we have a parallel connection as well, and again what we have to calculate is the active, reactive and apparent power components through each load first and then through the entire load. Again, so what we're going to do here is first we are going to consider each load as individual loads and calculate their apparent, active and reactive powers. Then we are going to consider the entire load and calculate the apparent, active and reactive power. Right, it's really simple, same as the previous one, so maybe you can do it by yourself. And fortunately here I have already found the current and voltage values to each component. So actually we have done this in the previous section 2.2. so you know the values, the voltage, current, the total impedance, current and current through each branch here, because here we have several branches and this branch has a different current value compared to this one, and the current here would be the summation of these two currents. This current, again this branch has, let's say, I1 and this one has I2, then the current here, this current will be the summation of these two. Right, so you already know these things, and I hope that you know, but if you still don't know, it's high time to go through the section 2.2 again. Right, and now answering the part A, it's same as we did before. So to calculate the apparent power, you need to know the voltage and current through the resistor. So resistor element we are talking here, and you know VR, and you need to know the current to this branch, right? And VR, okay, we already know what VR is, and the current to IR or IL branch. So current to this branch, we have current to this branch, we have already calculated, it's here. So once you know these two things, you know how to calculate apparent power. And for the resistor, we get the apparent power in that way, this much, I'm sorry. And again, so in this case you must notice that I'm using the Cartesian coordinates rather than polar coordinates. So it's sometimes useful to use polar coordinates, sometimes the other way. With the experience, you should get to know that which type of coordinates you are going to use. So even when you are using the calculator, it's sometimes better to proceed with polar coordinates, sometimes the other way. So in this case, I find it's better to proceed with the Cartesian coordinate, because if I am to use polar coordinates in this case, there would be more calculation errors, because calculator is sometimes going to in its computational logics, it's going to round up the values, and that rounding up may cause severe errors in my final answer. Therefore it's with your experience you should understand which coordinates to use, right? And so in this case, I can calculate the apparent power. It's going to be 6400 volt amperes. And now I'm going to take the real part out. That's going to be, you know, the real part out means I'm going to calculate the active power. And since the angle here is 0, so it's going to be a real number itself, therefore no worries. It's the same, it's 6400 watts. And if I take the imaginary part out, it's going to be the reactive power, so no imaginary part here, so imaginary part is 0, right? And therefore the reactive power consumed by this resistor is 0 watt, right? So in the same way, I have calculated the apparent, active and reactive power for each element. So for the capacitor as well, we have calculated. And one thing you should notice here, right? So when we calculate the reactive power of capacitor, you see it's a negative value, right? This is the case for capacitive elements. Usually you would the capacitive elements usually would result in negative power consumptions, negative reactive power consumptions, while inductive or as inductors simply would result in positive power reactive power consumptions, right? So that is something you should notice in mind. And yeah, so going to the second part, when you consider the entire load, right? So here as well, the entire load means you're considering these three elements together, which means the supply voltage and the supply current is the components you are going to consider in this case, right? So this is the supply voltage and the total current. So total current, we have found it here, this one. So it's going to be the summation of this value here and this value here. So these two together would form this, right? So once you know these values, you can easily calculate the entire load values. So in the same way, by using complex form of voltage and current, so you can calculate you get the active power as 6400 and reactive power as 4800, right? And that's it. So going to the discussion of this section. So again, if you look carefully what has happened by comparing the results from the part A and part B. So in the same way as we did before, if we compare, you can clearly see the results are the same. So one reason for this is that in our calculations here, on purpose I used the Cartesian form in these steps. As you can see here, here and here, when I happen to multiply complex numbers, I used Cartesian form. So in that way I could minimize the errors in the calculation, right? So therefore it's the same answers I get from part A and part B, right? That's one thing. And the next thing is here as well I can prove that the total active power is equal to the summation of individual powers here, right? Individual active powers, when I add them up, it's going to be the total active power consumption, right? In the same way, if I consider the total reactive power consumption, which is here, the total reactive power consumption, it's going to be the total reactive power consumption is going to be the summation of individual reactive power consumptions. So 12,800 minus 8,000 is going to be 4,800, right? So it's correct. And at the end, you can clearly see your total apparent power is the total active power plus the total reactive power as the imaginary part, right? So that relationship is going to be true for this case as well. So we can prove that the relationship is true by taking this value here and this value here. So then we get the total apparent power. And in the same way, if I happen to calculate the total apparent power, right? So here we have the individual apparent powers, and what I'm going to do is add them up using the calculator as complex values, So here it has 6,400 plus 12,800 angle is 90, which means 12,800 I minus 8,000 angle is 90 means minus, so 8,000 minus 90 degrees means minus 8,000 I is equal to this much. And if I convert this to this form, you get the same apparent power here, right? So it's the same apparent power. Or in the Cartesian form, it's same. So in either way, so the same number in Cartesian form is going to be here, right? So that those relationships you could prove that they are true, and they are going to be true for any case. So you first should understand this relationship, then you can apply this knowledge to sometimes to calculate unknown values, or else mainly to calculate unknown values, or to prove these relationships, etc. And it's going to be really important, right? And the next thing you should notice is we used Cartesian coordinates, therefore we got exactly the same answers, right? That's what I'm talking about. So you need to know which form from the polar and Cartesian should be used in order to get a better answer, right? And the first problem we used the polar form, and it caused some calculation errors in the two parts, part A and part B. So they were not an exact match like in this case because of the polar form. And the next thing is we have already noticed that reactive power in the capacitor is negative, that we have noticed, and by conversion this is true, and for any capacitor that would be the case for a capacitive load, and for an inductor. So simply this is what you need to note down. For a capacitor, the reactive power is negative, and for an inductor the reactive power is positive. So that's what you should notice. And as the fourth point, we saw that some of the reactive power consumed by the inductor, so the reactive power of the inductor is 12,800, and the capacitor is having a negative 8,000, which means it's delivering some of the power consumed by the inductor. So that's what it happened here. That's why the total reactive power is less than what is consumed by the inductor. So you can clearly see here is 12,800 and it has dropped down to 4,800 when you consider the entire load. That's because some of the power consumed by this is given by the capacitor. So the capacitor is supporting the inductor. This is the idea. So that you should notice. And again, if you consider the current. So this causes a significant current change in the branches. If you consider the currents through the individual branches, right? So that's what we are discussing here. The total current is the total current magnitude is, if you consider, just 20, but the IC branch alone is having a 20 ampere current, and IR and IL branch is having this much of current. So if you consider about the magnitude values, 35 point something, which is going to be 35.78 plus 20 would be the magnitude wise summation of these two currents, this current and this current here, right? So those two currents respectively are 35.78 and 20. But you would notice that again the current here, the total current, right, which is same here, is 20, just 20 in magnitudes, right? So it's better if we could show this on a complex plane. So this is what it is meant. Sorry. On a complex plane, I would try to draw a picture which is as clear as possible, and I'm going to use blue color for my total current. It's negative 30 something, 20. This is I, and green for the capacitor current. It's simply plus 20, which means this much. Right, and now the current through the resistive inductive branch is going to be again a negative angle with 35 something, right? This is what we are talking. This is IR, OL, IR, OL, so it's a series combination, and in this case this is IC, right? So in vector summation you would notice that this IRL is the exact difference here, right? So this length here is equal to IRL, because the summation of IC and IRL should be I. So the summation of IRC and IRL is equal to I. So I hope it's clear. So the idea is that the drawn current from the source has reduced because some of the power required by the inductor is now delivered from the capacitor, which means there is a current which is oscillating in this branch, right? So there is a current which is oscillating between these two branches. It's not injected to the total current branch. This current is not going to the source side, but instead that current is oscillating between the inductor and the capacitor here. So that's why these currents are higher than the current drawn from the source, right? So I hope the idea is clear now. Right, so this is the end of the first part about apparent power, active power and reactive power, and yeah, I hope you got a clear idea